next speaker is Dr. Daniel Mira Martinez. He's currently the head of Propulsion Technologies Group at the Computing Applications for Science and Engineering Department at the Barcelona Supercomputing Center. Dr. Mira received his bachelor degree in mechanical engineering from University Politecnica Valencia, and then got his PhD from Lancaster University. He joined the BSc in 2013, and from what I know, he has been currently leading the effort of the Center of Excellence in the EU on the exascale computing for turbulent combustion simulations. So today he is going to talk about some digital models for energy convergence systems. So,
okay.
All right, the floor is yours.
Okay, thank you very much. Thank you for the introduction, and thank you for the invitation. It's a great pleasure for me to be here. So I'm just going to give you a small overview of the different activities that we are doing in our group, going from classical CFD, classical CFD to machine learning assisted CFD, and also extending applications. So first, let me just introduce that I work at the Barcelona Supercomputing Center. We are located at the city of Barcelona in the northeast of Spain. And the main characteristic of our center is that we host the supercomputer Mare Nostrum, that is one of the largest infrastructure for supercomputing in Europe. We are in the process of upgrading to Mare Nostrum 5, that will be one of the 3 exascale systems that Europe is putting into place. So among the different activities, we see that we have seen in this conference and throughout the days that there are many applications where machine learning can be used and artificial intelligence, for example, for closures, for physical modeling, physics extraction, reduced order models, and digital twins. And this is something that is bringing a lot of attention today, but the main thing is that it requires computational power to do that. So for different aspects or for different elements of these applications, you need to interact with the hardware, and you need to make this very efficient. So this is why most of the leading activities in machine learning has been conducted by computational scientists, at least in our institute. But now we are more application-driven researchers, and now we are trying to incorporate all these methods and methodologies in our day-to-day application. So I'm going to try to explain a little bit of what we are doing on this. So as you know, the combustion process is a complex physical system, and it requires many different physical elements. So you need to include for fuel injection, atomization, evaporation, ignition. But if you want to model with high fidelity these systems, there are many uncertainties regarding the boundary conditions when you look at realistic configurations. And also on the modeling side, we need to rely on simplification and hypotheses to make the simulations feasible. So indeed, this is really a good opportunity for machine learning models that can be helpful to provide new closures. And this is something that the community is exploring, and this will be very important in the future. However, there are some challenges that I think they have been already discussed so far in the conference. So we need to access reliable data sets, no matter what is numerical or experimental. So you need to deal with data that has different formats, different standards. So you have to manipulate all this data to work with this. This is not simple. This takes time, especially when you have large data sets. Then you have to identify the proper machine learning algorithm for the application that you are interested in. And then a second step is the training process. So you need to develop a model, but you need to do the training. And this training can be expensive and costly, and you need to come up with good ideas in order to make this feasible. And finally, that I think is not less important than the others and not less complex, it's just the opposite, is if you want to do CFD simulations or high-fidelity simulations with this machine learning model, you have to instrument your code, you have to prepare your code to run with these models. And this is also another element that it brings a lot of relevance, because you are worried when your simulation takes a millisecond or seconds per time step. If the part related to machine learning is taking much more time, you will not going to be happy in your CFD. So this is something that we will have to deal with, and this brings some challenges. So there has been quite a lot of literature on how to incorporate machine learning models for combustion, for turbulent flow. So there has been quite a lot of effort developing specific models, and also some review papers that cover, I try to give you an overview of what has been presented. So in very short time, there has been a lot of progress on this field. So in our group that we're mainly working on CFD applications and high fidelity modeling of combustion system, we're trying to see if what machine learning can help us to improve in our model. So the first application that we were going to look at is, for example, how we can predict pollutants, in this particular case, NOx emissions, when you have hydrogen flames, and also in the context of tabulated chemistry. So you know, or has been briefly introduced, tabulated chemistry is an efficient method to simulate combustion systems because it's very cheap. You rely on the tabulation of certain properties, and this reduces substantially the computational cost, but it doesn't give you the flexibility that you need and the accuracy that you need for certain particular physical aspects. And this is something that we're trying to explore in our group, and basically what we're trying to do is, okay, if we are happy with our tabulated chemistry for solving certain flow, if we are not happy with the results, for example, from the NOx, is it possible to decouple the NOx model from the tabulated chemistry and solve the two problems at the same time? Is this possible? So we try to do that, and basically, let me just give you a short explanation of what tabulated chemistry is, for those of you that are not familiar with this concept. So basically, in the first step, you identify a canonical configuration, preferably in a one-dimensional domain that reproduces with certain fidelity the combustion process that you are interested in. In the second step, basically, you just build a database based on these solutions, and you identify some controlling variables that can represent the composition space. And then you perform some methods to account for turbulent chemistry interaction or subgrid treatment. And finally, when you have this database based on the function of these controlling variables, basically you couple this with your CFD, you load this table in your numerical simulations, and then you just run the code recovering the properties that are tabulated. So in the end, it's very cheap because you don't need to compute anything. Everything is pre-computed, but you need to recover the information from the table, okay? So when we deal with NOx formation, in particular case of hydrogen flame, but in general for NOx, you have to deal with different time scales that come from the pollutant formation process. So, for example, you have to deal with fast species that are related more from the heat release and the combustion process itself, but also you need to deal with slow developing species that are more related to the pollutant formation. For example, a common approach that is used for modeling hydrogen flames with tabulated chemistry is to define a progress variable that is based on the water, so you have somehow a good prediction of the different thermochemical structure of the flame. However, this definition sometimes can bring to some problems, especially in rich burn conditions or when you deal with, for example, slow developing species and also enthalpy effects. So the idea is that if somehow we can solve our mixed fraction and progress variable problem with the tabulated chemistry, and then to add an additional transport equation that can represent the NOx formation, then this could bring some decoupling between the chemistry and the emission model. So the question now is this source term if possible, to compute it directly from the Flamelet database, or can we use a neural network that will provide this source term? Is this more accurate? Is this faster? So these are the questions that we were asking ourselves when we started this investigation. So in general, we can discuss that if we deal with NOx formation, there is a real disparity in the temporal and spatial scales of the flow. For example, for oxidation, you will end up in orders of magnitude of the time scales depending on the definition in the 10 to minus 5, 10 to minus 4 seconds. However, for time scales for NOx, it's in the order of 10 to minus 1. So this is a large disparity, and this is not simple to deal with tabulated chemistry. So there has been some effort in the literature to deal with this problem. So one possibility is to somehow to describe the combustion process by definition of a progress variable, and when you are approaching near equilibrium, then you change the definition to account for the NOx that is formed more or less near equilibrium. That is a very well valid approach and has been used several times, providing good results. Another possibility that brings an additional simplification is just if somehow you can include the NO mass fraction, for example, in the definition of the progress variable, so you can get some sensitivity even near equilibrium in the progress variable related to the evolution of the NOx. So in this work, our idea was mainly to say if we can have a definition for the source term for NO that can be useful and couple providing accurate results for this. So how we started? So basically, like any simulation that requires tabulated chemistry. So we first consider the thermochemical or the operating conditions of the burner. In this case, it's an atmospheric burner operated in preheated conditions, and it's a mixture between air and hydrogen. We use the San Diego mechanism to describe the chemistry. And basically, what we did is to run 1D laminar premix flames at different equivalence ratio to cover the whole flammability range. And this is what you see here in the figure. So you cover from the temperature, flame thickness, laminar flame speed, and this is what you have for the NO, the equilibrium NO in this case. So then on the second step is, okay, if we want to develop a neural network based on this, we need to define what architecture we are going to use for this problem. So we play around a little bit with different definitions based on the data in the literature, and then we found that just trying to work with normalized quantities gives you a little bit better flavor of how the things are working good or are working bad. So basically, we consider the mixed fraction, the normalized mixed fraction, progress variable, and also the NO. And then we play around with the size of this neural network, and then we satisfied with 2 hidden layers of 16 neurons, and somehow this was giving us relatively good results. And then we also play with this size to evaluate the performance. But the output at the end was let's say, the chemical source terms related to NO. So then, of course, we have to do the training, and then the training was at the end successful with considering these definitions. So we were able to somehow develop a model that can actually reproduce the evolution of NO in your system. So as a first step, of course, we wanted to validate this model in a priori assessment, and we were extremely happy to see that everything works. So it was really our first experience using machine learning on an application, and then we found that as the other people, we were successful on developing this model in the a priori assessment. But then, of course, we want to test this in a realistic condition. How this model that a priori assessment is very good, what would happen when you apply it into the real case? So for that, we prepare our CFD solver, and then we solve equations for the mixed fraction and the progress variable, and then we consider the tabulation of the chemical source term for the progress variable to resolve the chemistry problem. And then we compare different approaches. So the first one we call lookup. Basically, we obtain the mass fraction of NO as function of the mixture fraction and progress variable without using any fancy definition of the progress variable. So this is really going to fail, but we wanted to see how, if you are not careful, what will happen, no? And the second one is what I said. If we consider a transport equation for NO, and we provide a closure for the source term based on the tabulation of the flamelets, and then finally we do the same using the source term that comes from the neural network. So what you can see here is the results of this investigation. In order to account for the residence time in this, freely propagating flame, basically what we did is to have a very large domain, so this somehow can represent what happened with the residence time. And in this case, this is a small subset because what we did, it was an 8-meter domain, but doing a representation with this size, you can see exactly what happens. What happens is that when you are, in the near region of the flame, you don't see this very well, but all the methods behave very well because you are far from equilibrium, so all the approaches give very good results. However, when you are departing the time, the lookup is not able to recover very well the evolution of the mass fraction of NO, and the same for the source term, and the same for having an equation with a tabulated source terms for NO. However, the neural network was able to not only reproduce very well in the near part of the flame, but also for all the domain size. So it means that it was able to reproduce very well, or to account very well for the residence time, for the formation of NO with the residence time. So of course, we were, this was not the slide, but anyway. Sorry, that's my mistake, sorry. So we were very happy because we got very good accuracy with the model. So, however, then when we tested it, we realized that having this neural network model in our CFD was slower than accessing our flamelet database. So indeed, if you are going to work with these models, you need to prepare the code to be efficient when dealing with these simulations. So in fact, when your neural network is small, then there is no overcost and the CPU works quite well. But then if you have a very large neural network, then you're going to suffer, and you need to be very careful on how you deal with this, no? So in this process of increasing the fidelity, we've been really pushed by the fact that we need to have more physics, and we need to have better understanding of the physical system, and include this understanding into digital models that can be used to predict real physics in real systems. So for instance, in this, we have now a new project that has recently started, that we want to develop a digital model of a reheat furnace, for example, and this is a very, very complex system. So you have the steel billets entering here, you have these long flames, these super big flames here, so you can be very accurate predicting the flame and the atmosphere of the furnace, and eventually you can be very accurate predicting the heating of the billet, but then you need to account for all these processes. So if you really want to have accurate prediction for what's happening in this big system, CFD by itself is not going to help you very much, because you have many unknowns and you have very complex physical problems, and this can result extremely expensive using CFD. So in the end, you can be very accurate for predicting individual physics, but not for the whole thing. So the question is it possible to develop a model that can take into account high fidelity modeling of the subsystems, but also accurate predictions for the full system? So, well, this is something that we really need to do. And indeed, what we have seen over the years is that the simulations can really make a substitution of the experiments, but not at the whole level. But this can be used to reduce the experimental testing. But in the end, sometimes you realize that doing experimental testing is less costly and much faster than doing simulations. So at the end, we need to have digital models that can predict the physics, but from real systems. So we need information from the system itself. So we need the information from sensors. But also, if we want to develop models that can assist on design and optimization, these models need to be real-time. And of course, there is a variety of models that we can use for this. And then we need to develop appropriate platforms and workflows that can incorporate all these models. So on this, this is something that we have been exploring in our group. So we had an European project also to try to develop emissions model for microscale urban flow. So basically, what we did is we collected the CAD files of 30 cities in Europe, and then we developed more than 400 emission scenarios. And then this ended up with more than 20,000 samples that we do the training of the model, considering 1 meter resolution in the flow. And then we required a lot of intensive calculation with more than 6 million CPU hours using 2,000 CPUs to compute all these flows. And then finally, we were able to develop a neural network model that can provide information what would happen about the dispersion of these pollutants throughout the city, just using a single GPU. So at the end, this model is very good because with a single GPU, you are able to describe the emission patterns that you will have on different cities without having a priori knowledge of which city you are interested in. At the end, the error, well, I think it was presented by, in the morning, was discussed what the error is. And this error seems very high, but considering the uncertainty that you have in the dispersion of pollutants in a city, 15% is something that the people in the town hall of the cities consider appropriate. So in this, we've been trying to look at also forecasting for power plants, solar power plants, and also other type of applications in which we develop models and we couple these models with an infrastructure for testing, and this is something that we will be doing more and more, even with our background in high-fidelity modeling and simulation. So with this, I just come to the conclusions, and well, I think in summary is what has been said in the conference so far. There is a real demand on incorporating more physics into the models. So we are okay at predicting single physics, small subcomponents of complex physical systems, and really it is through the use of machine learning and artificial intelligence where we should be able to try to provide reliable and predictive models for full systems. And of course, this would require a lot of effort on our side, and of course, we will need to rely on how we interact with the supercomputers and the hardware architectures. And with this, I'm just happy to take any question and discuss with you.
Okay. Oh, right there.
Thank you. It was really nice talk.
Thank you.
Thank you very much. So can you just go to slide 18 and then just, I wanted to understand a little bit more. You mentioned about 6 million CPU hours or?
Yeah.
And these are to run the digital twins at those mentioned locations. But
yes, so yeah, so basically we just get the CAD file of the city, we mesh it, and we run the simulation.
So basically it's at the finite volumes of the mesh locations, you just ran the digital twins.
Exactly. So basically we do CFD modeling, considering incompressible Navier-Stokes equations, plus an additional transport equation to describe the pollutant that is emitted from a given source. And then we consider different scenarios from this source and different wind distributions in the city. And with that, we develop this database of the models.
And the model is currently it is implemented and then just it's running, and meaning like, okay, it's using?
No, it's not real time. So it's a separated thing. So we run all these individual simulations, and then from this database, we extract some samples. And then from those samples, we develop the neural network. So the testing of the neural network was with the samples that we didn't use, and we were trying to see how accurate this neural network was to trying to explore the parametric space that we didn't use for the training. Okay. That was the whole idea.
Thank you very much. So we'll discuss.
Paulo?
Sorry, I didn't understand thank you for the presentation, it's extremely interesting. Sorry.
Thank you.
I didn't understand well how you use the neural network to calculate the source term in the equation, because if you use it on the tabulation basically, then you run the neural network and then you recover the outcome, what you expect, which is the source term, right? So why would it be slow, and why would you run it in real time? So why would you run it during the CFD simulation? This is what I don't understand.
Okay, yeah, maybe I didn't explain this well. Okay, thank you for the question. So yeah, the surprise was that this neural network. So we couple PyTorch with our CFD code, and then we develop this neural network, and this is an input file to the code, and then we just recover. So the neural network uses these three parameters: the local mass fractions of NO, mixture fraction, and progress variable, and it gives you back a source term. Okay, so this operation, perhaps with the framework that we developed, was very slow compared to the accessing the Flamelet database with these similar input parameters. Was 1 order of magnitude faster. So what I understand and this is something that we're working on at the moment, is to understand why it's so slow. And I think it's just how the interconnection and how the interconnection of the neural network is when it's executed in the CPU.
I got it. So I understand why. Probably it was running. So the neural network was running during the CFD simulation.
Yeah. It's exactly.
You could find a function, explicit function, x1 times a. You find the a, b, c, and d. I mean, that would be probably faster.
Yes, probably that would be faster. Yeah, if we decouple the PyTorch environment and we do.
Embedded in the simulation. Okay.
Exactly.
I got it.
But the idea was that to make it flexible, because maybe you can develop a better NOx model for me, and we use the same format, and then we just plug it in.
Okay, got it. Thank you so much.
Okay, thank you. Yeah.
Thank
In
you.
the back.
On Paulo's so why don't you? I mean, the three conditions that would it be maybe pressure, temperature, and equivalence ratio?
Yeah.
Why don't you take these packages outside, or they in and outside of that model, and build up that table and run your CFD on it? Yeah.
Yes, that would be
Again, I mean, I'm just thinking of temperature, pressure, and equivalence ratio condition not being so massive and gigantic. So why not?
Yeah, the idea is to develop a demonstrator for a very simple problem that we have full control, and see what were the computational bottlenecks.
And then
so exactly. So now that we have identified them, we are trying to correct them. So it means that now we should be able to have a much more complex model where, for example, there is information in the code that we don't have and can be generated with a neural network. But indeed, you are totally right. I mean, this
can be done simpler. Yeah, but
it's a simple problem. It's a toy problem, but has a lot of implications in terms of development, analysis, and performance evaluation.
The target is to generalize it, of course.
Exactly.
With the fast processing neural network.
Exactly. Thank you. Yeah. Thank you.
Okay, I think it's a good discussion spent. All right, let's thank our speaker again.
Thank you.